Welcome to This Explainer. Let's jump right in. Today, we're taking on a comprehensive masterclass on machine learning. We are definitely going to explore the theory, but more importantly, we're looking at how building practical, hands-on projects with actual source code is literally the ultimate bridge between studying concepts in a textbook and actually landing that next job or internship. Because, let's be real, there's a massive difference between just knowing what an algorithm is and proving you can deploy it to solve a real-world problem. And that is exactly what we are focusing on today.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the core of machine learning, move into supervised and unsupervised learning, and then elevate things by building deep neural networks. After that, we'll decode natural language processing, and finally, we'll talk about exactly why building practical projects matters for your career. Don't worry if this sounds like a lot. We're going to build your knowledge block by logical block with absolutely no overwhelm.
Section 1. The core of machine learning. Let's start right at the beginning and set up our very first foundational block.
At its absolute core, machine learning is a specialized branch of artificial intelligence. Think about it. Instead of relying on a human to sit down and tediously write thousands of lines of manual, explicit, rule-based instructions, we use algorithms and statistical models. These systems dynamically analyze massive volumes of data to spot underlying patterns and correlations. Through this data-driven learning process, the models actually improve over time to generate highly accurate predictions on entirely new, unseen data. It's incredibly powerful because it literally adapts as the data evolves.
But here is the catch. Algorithms are really only as good as the data you feed them. They absolutely need high-quality inputs. And that makes data preprocessing, and specifically feature engineering, the critical foundation for building robust, reliable models. Feature engineering is the art of creating, transforming, or selecting relevant features from raw data to highlight meaningful patterns. If you engineer your features well, you basically bridge the gap between messy real-world data and the algorithm, massively improving your model's predictive accuracy.
Section 2. Supervised learning in action. With our data prepped, let's move to the most fundamental and widely used branch of machine learning. The core divide in how models learn is actually pretty fascinating. On one hand, you have supervised learning, where models are trained on labeled datasets with known answers. The model essentially learns by guessing, checking how far off it was from the correct answer, and then minimizing those prediction errors over time. Contrast that with unsupervised learning, which tackles totally unlabeled data to find hidden natural structures all on its own, without an answer key. Now, if you want to build a supervised learning system, say a financial fraud detector or a healthcare diagnosis model, there is an exact 8-step life cycle you'll use. You always start with defining the problem and preparing your data. Then, and this is absolutely crucial in step 3, you split your dataset into training and testing sets so you can actually prove the model works on unseen data. After selecting and training your model, you evaluate it, deploy it into the real world, and continuously monitor it to ensure it stays accurate over time. This is the absolute gold standard framework for any practical project.
Section 3. Patterns in unsupervised learning. Now that we've mastered labeled data, what happens when we just don't have the answers up front?
Well, this is where unsupervised learning really shines. Think of it like a detective finding hidden clues in a massive pile of information. Let's talk about some of the most popular clustering algorithms. K-means is fantastic for dividing data into distinct groups, which is perfect for customer segmentation and marketing. Hierarchical clustering builds this really cool tree-like structure, often used in genomic data. And then there's dbScan, which groups data based on density. That means it can find clusters of completely arbitrary shapes and is excellent at spotting outliers, making it a total go-to for anomaly detection in cybersecurity.
Unsupervised learning also tackles something with a rather ominous-sounding name, the curse of dimensionality. It sounds scary, but basically as you add more and more variables to a dataset, the data gets sparse, making it incredibly hard for algorithms to find patterns. Enter dimensionality reduction. Clever techniques like PCA, TSNE, and UMAP simplify these massive datasets. They reduce the number of features to save you massive computational costs and speed up training, all while seemingly magically preserving the most significant information and the underlying structure of the data.
Section 4. Building deep neural networks. All right, let's elevate the technical complexity a bit and step into the fascinating world of neural networks. Deep learning is a highly specialized branch of machine learning that's actually inspired by the structure of the human brain. So instead of manual feature engineering, deep learning uses multi-layered neural networks. These consist of input layers, multiple hidden layers, and output layers, which automatically learn hierarchical features from complex, unstructured data.
This right here is the powerhouse technology behind advanced tasks like image recognition, autonomous vehicles, and speech recognition.
Building a neural network from scratch in a language like Python follows a very specific mathematical workflow. You initialize your random weights and pass your data forward through the layers to get a prediction. That's your forward propagation. You then compute your loss, basically measuring just how wrong that prediction was. Step 4, backpropagation, is where the real magic happens. The network calculates the gradients of that loss and propagates the errors backward. It then updates its parameters, adjusting the weights to be slightly more accurate, and just iterates this process over and over until the model converges on the right answers.
Within those hidden layers, we have activation functions. You can think of these as the decision makers of the network. They determine whether a neuron should fire or not, allowing the network to learn really complex, nonlinear patterns. Now, while sigmoid and tan are your classic choices, ReLU, or rectified linear unit, is incredibly popular because of its sheer computational efficiency. Though, humorously, ReLU does have a quirk, where its neurons can occasionally just die and stop updating entirely if they're fed too many negative inputs during training. Softmax, meanwhile, is typically used at the very end of the network to turn outputs into easy-to-read probabilities.
Section 5. Natural Language Processing Explained. Let's shift our focus to how these advanced models actually manage to process, read, and understand human language.
Natural language processing, or NLP, is the AI capability that bridges the gap between human communication and computer understanding. Think about the absolute mountains of unstructured text we generate every single day: the emails, the reviews, the social media posts. NLP systems can scan, interpret, and generate language naturally. It saves an unbelievable amount of time by automating tasks like sentiment analysis to gauge customer feedback, machine translation to break language barriers, and of course spam detection to keep your inbox clean.
Now, what's really interesting about evaluating text classification models is that you might think basic accuracy is all you need, but consider the concept of the confusion matrix, mapping out true positives against false positives. Imagine you have a highly imbalanced data set. Say only 1% of emails are actual spam. Well, a model that blindly guesses not spam every single time will technically be 99% accurate, but it's completely useless. That's exactly why we have to rely on metrics derived from that matrix, things like precision, recall, and the F1 score, to see exactly where the model is getting confused and get a true, honest picture of its performance. Section 6. Why practical projects matter. Okay. We've covered some incredibly complex theory today. Let's bring it all back down to earth and answer some of your most pressing career questions.
Let's kick off a rapid-fire FAQ, starting with the absolute most common beginner hesitation. Do you need a master's degree in computer science and decades of coding experience to start building these machine learning projects?
The answer is a resounding no. Basic Python knowledge is truly enough to get started. Python is the industry standard precisely because it's incredibly beginner-friendly and readable. When you pair Python with standard, powerful open-source libraries like NumPy for numerical computations and Pandas for data manipulation, you literally have all the tools you need to load a dataset, process it, and start training models immediately.
Which leads us to the next massive question for anyone looking to enter this field. If you build these projects, are they actually useful for job interviews? Do they move the needle when it comes to getting an internship or a full-time job?
Absolutely. In fact, it might just be the most important thing you can do. Having a portfolio of practical projects with clean, modular, well-documented source code is the ultimate proof of your hands-on skills. It validates your methodology. It proves to hiring managers that you don't just know the buzzwords, but that you actually know how to clean messy data, select the right algorithms, avoid overfitting, and apply theoretical math to solve real-world problems.
So, we've walked through the fundamentals today, from data pre-processing and supervised learning all the way to deep neural networks and NLP. You now understand the life cycle of how these incredible systems are built. The only question left is for you. With these building blocks now in your mind, what complex, real-world problem will you solve with your very first machine learning project? Don't wait. Find a dataset, open up Python, and start building today. Thanks so much for joining me on this explainer.